Hello everyone, I'm Yuanliang Chen from Tsinghua University. Today, I'm going to introduce my recent work, CAFault, a testing framework for enhancing existing fault injection technique in practical distributed systems by generating plenty of fault-dependent configurations. Distributed systems are everywhere, from distributed file system, distributed database, to distributed computing framework and distributed machine learning. They help handle large-scale data, keep things running across many machines. Where distributed environments are complex and dynamic, where failures happen frequently. When they do happen, the consequence can be serious, often leading to significant economic losses. There are many different types of failures, such as network delay, package loss, node breakdown, disk fault, and so on. Consequently, the economic losses caused by distributed system failures have been increasing year by year. To deal with these everywhere faults, distributed systems have all kinds of fault tolerance mechanisms to keep service reliable and available, even when something goes wrong. However, because distributed systems are so complex, it's easy to make mistakes when handling this kind of failures, either due to wrong logic or bugs in the code implementation. And we call these issues fault handling bugs. To find these bugs, researchers have built a number of fault injection tools that simulate and inject different types of faults into distributed systems. These tools have been quite successful. They have already detected many real-world bugs. However, most existing fault injection tools test distributed systems under fixed and default configuration setting. They don't really consider how different configuration settings might affect how the system handles faults, which means they could be missing a lot of important bugs. In real-world applications, system configuration plays a key role in helping distributed systems run reliable under different conditions. It gives the systems the flexibility to adapt to various scenarios. In these systems, configuration inputs define how the system behaves. What's important is that some configuration settings are closely related to how faults are handled. We call these fault-dependent configurations. They can greatly affect the results of fault injection testing. Unfortunately, most existing fault injection tools don't really take this into account. Well, to catch more fault handling bugs, we need to go beyond traditional fault injection tools and bring in a wide range of fault-dependent configurations. In other words, we should test the system's fault tolerance mechanisms under different configuration settings using fault injection technique. That's how we can better detect hidden bugs. However, testing with both configuration inputs and fault injection inputs at the same time is really challenging. Distributed systems usually have tons of configuration parameters, so the configuration input space is really huge. On top of that, fault injection inputs like when to inject, where to inject, and how long the fault injects also create a large input space. As a result, combining these two makes the overall input space extremely large and hard to explore effectively. Since the combination of these two input spaces is significantly huge, to effectively detect fault handling bugs hidden in distributed systems, there are two main challenges. The first challenge is figuring out how to automatically analyze the hidden dependencies between fault inputs and configuration settings, so we can narrow down the configuration input space. In practice, many configuration items do not affect fault handling logics and can be skipped during testing. But because there are so many configuration options and their meanings are often complex, it's hard to automatically tell which one actually matter for fault handling logics. The second challenge is how to smartly explore and narrow down the fault injection input space. For a given configuration setting, faults can be injected at any time and any point in the system's execution process, which means the input space are mostly infinite. So we need an effective way to help explore this space during testing. Well, to overcome these two challenges, we propose CAFault, configuration-aware fault injection technique, a testing framework for enhancing existing fault injection technique by generating plenty of fault-dependent configurations. Here is the overview of the CAFault. It contains two main processes: fault dependency construction for processes and fault handling guided fuzzing process. The first process focuses on building the FDModel, the fault-dependent model, by observing how dynamic coverage changes when we test the system with different combination of faults and configuration inputs. This helps us understand which configuration item actually affect fault handling logic. It's worth to know that in this process, we don't need to precisely know each coverage number to each fault operation. We just need to observe whether there is any change in coverage. That's enough to guide the process. If current configuration leads to new coverage improvements in the fault tolerance mechanisms, it is regarded as a high-quality configuration, and then based on it, CAFault proceeds to the second step. The second step is the fuzzing test process. For each given configuration setting, the fault injection space is still huge. A commonly used method such as CrashFuzz tries to handle this by use runtime code coverage to guide fault injection input generation. But increasing code coverage doesn't mean we are actually testing the fault tolerant logic. It often ends up exploring unrelated code execution. Instead, CAFault takes a more targeted approach. It directly uses the code in fault tolerance mechanisms as feedback to guide fault injection, making the testing more focused and effective. If the coverage starts to converge, meaning new fault sequence no longer trigger more fault handling code, CAFault goes back to the first step to re-explore and update the FDModel. Then it selects another high-quality configuration and continue with the next round of fault injection fuzzing process. This way, CAFault keeps learning and testing more effectively. CAFault uses dynamic runtime information to keep learning these hidden dependencies so it can constantly update and improve the FDModel. The key idea here is if we inject the same fault input but change a configuration item, and that causes a change in execution coverage, then we say this configuration item and this fault input are dependent to each other in how they affect the system's execution behavior. Well, since changing just one configuration item at a time is too slow, to speed up the learning process, CAFault mutates a group of configuration items together. For each fault input, we observe whether this group causes any change in coverage. If it does, we then use a binary search-based minimization algorithm to narrow down the smallest subset of items that actually trigger the difference. Unlike existing fault injection tools, CAFault directly uses the code in fault tolerance mechanisms as feedback to guide fault injection. To do this, the first step is to automatically extract the parts of the code related to fault tolerance from the coverage data. We use static analysis technique to identify and mark the code related to fault tolerance mechanisms. Considering that in most distributed systems, Their fault tolerance mechanisms typically involve the capture and handling of all kinds of exceptions. So the first step is to statically scan the source code of the system under test to identify all exception handling code blocks. Then we use the fault handling code coverage to help guide the fault sequence input generation. The key process here is that for a given mutated fault sequence input, CAFault injects it into the distributed system under test with executing the same workload. If this fault sequence contributes new fault handling coverage or leads to the discovery of new bugs, it is regarded as an interesting seed and is stored back into the seed pool to help guide the next fuzzing iteration. We implemented CAFault on 4 widely used distributed systems: Hadoop file system, ZooKeeper, MySQL-Cluster, and IPFS. We choose this system because they are not only popular, but also diverse. They come from different organizations and are implemented in different programming languages. By testing across these systems, we show that CAFault is a general testing framework, is cross-platform, language independent, and works well across different distributed systems. This picture shows the core components of CAFault, which can be divided into 3 main parts. First, we have the configuration generator. Its job is to create high-quality configurations that actually affect how the system handles faults. Second is the fault injector. This part explores different fault inputs under each configuration setting, helping us test how the system behaves when things go wrong. And the third is the interaction adapter. This is a bridge to the system under test. It defines the configuration input format, sends workloads, and monitors for any abnormal behaviors. To evaluate the effectiveness of CAFault, we run it on 4 widely used distributed systems. We conduct several experiments to address the following 4 research questions. The first question is CAFault effectively in finding fault handling bugs of real-world distributed systems. We run CAFault on 4 distributed systems, including HDFS, MySQL-Cluster, ZooKeeper, and IPFS. In total, CAFault successfully detected 16 new error handling bugs. Well, since the existing tools only perform testing on the fixed and default configuration setting of the distributed systems, to provide a fair comparison and validate whether FDModel can enhance the testing performance of existing fault injection tools. We also integrate FDModel into these tools, which we refer to as CrashFuzz Plus, Mallory Plus, and Chronos Plus. The results shows that the fault-dependent model really helps improve bug detection. Compared to other state-of-the-art tools, CAFault not only found all the bugs they found, but also detect additional ones they missed. The second question is, can CAFault cover more fault-tolerant logic in distributed systems compared to other state-of-the-art tools? Well, to evaluate the effectiveness of CAFault in covering fault-tolerant logic, we compared CAFault with 3 state-of-the-art fault injection tools: CrashFuzz, Mallory, and Chronos. In conclusion, CAFault always covers more fault handling code than these tools. Also, if we look at the coverage growing over time, the test coverage of CAFault is actually smaller than other tools during the first 8 hours. This is because CAFault spent time in the first step analyzing runtime coverage and constructing and updating the FDModel, which introduced some overhead. But once the FDModel is completed, around 8 hours, CAFault's coverage starts to quickly go beyond the others and stays constantly higher from that point. Next question, how effectively does the fault-dependent model, FDModel, enhance testing performance? Well, to evaluate the effectiveness of FDModel, we also conduct the experiments that compares CAFault with CAFault minus, the version of CAFault which disable the fault-dependent model and generate configuration input randomly. From the table, we can find that with the help of the FDModel, CAFault can detect all 16 bugs in 48 hours, while CAFault minus only detects 7 of them. Besides, CAFault also achieves higher fault handling code coverage than CAFault minus. Therefore, we can conclude that the fault-dependent model can effectively improve testing performance in both bug detection and fault handling coverage. Well, the final question, to what extent does fault handling guided fuzzing improve the performance of testing? To evaluate the effectiveness of fault handling guided fuzzing algorithm, we conduct the experiments that compare CAFault with a version that randomly injects faults and another version that utilizes traditional code coverage guided fuzzing strategy. From the table, we can find that with the help of the fault handling guided fuzzing algorithm, CAFault can achieve better testing performance in both bug detection and fault handling coverage. Well, our future work will mainly focus on the following 2 directions. First, we would like to improve our FDModel construction process. Since dynamic learning process introduces runtime overhead, slowing down the initial testing speed, we would like to introduce static analysis technique to quickly construct an initial FDModel. For example, by constructing the abstract synthetic tree of the system's source code and analyze the retrievability between configuration item and the fault handling logic. However, such initial model can bring in a lot of false negatives as well as false positives because static analysis doesn't fully capture dynamic behaviors like multi-threading and async events, which are commonly used in distributed systems. So we then plan to utilize dynamic analysis in CAFault to refine the initial model and reduce false dependencies. Second, we would like to design more Oracle to help support more bug types such as load imbalance bug, consistency issues, and so on. Take load imbalance bug as an example. This happens in distributed system when the workload or data isn't distributed evenly, which can hurt performance, waste resources, and reduce reliability. CAFault can help by first figuring out the configuration item related to system load setting, then mutating them to generate high-quality configuration. Using this load-dependent configuration, it can effectively detect imbalanced bugs. Thank you for your listening. Any question?